Hello, and thank you for joining us today. I am your host, Shannon Hicks, and welcome to the webinar, Using Advanced Analysis and Measurement Techniques to Tackle the Tough Noise and Vibration Issues of Electric Machines. Now, before we begin the presentation, I would like to review a few housekeeping items with you. Please take a moment to observe the tools you have available in the WebEx event window. There is a chat panel for any technical issues like audio or visual. And if you have any questions for the presenters, please utilize the Q&A panel. Our presenter is Corinne Degrandel, is a EOMYS engineer as NVH R&D engineer, specialized in acoustics, and then Ed Green has a PhD from Purdue University and is a principal staff engineer at HBK Sound and Vibration. I would now like to hand it over to Corinne to start the presentation.
Yeah, thank you for the introduction. So I will be starting by introducing EOMYS company first. So EOMYS has been created 9 years ago and is located in north of France, very close to Belgium border. We do engineering consultancy specialized in NVH of electrical system. So there are 15 employees in the company, all specialized in a specific field, either electrical engineering, vibroacoustic, or scientific computing. We have our applications are mainly focused on transportation, but also on energy, home and medical appliances and industry. So what we do at EOMYS is we propose a large choice of consulting services, starting from troubleshooting of NVH issues in electrical system. So it's mainly done via measurement, but also simulation. We also optimize design of electrical system. So this is mainly based on simulation. On top of that, we provide some technical trainings on vibroacoustic of electrical systems, and we develop and distribute our own software, which is called Manatee. So globally, EOMYS can really work during the whole development cycle of electric powertrains. So it starts from design stage up to the final experimental validation. So why is it important to work on ENVH? Just choosing the topology of the machine or the slot pole combination of the machine, we've seen from EOMYS experience that it can have a large impact on NVH due to magnetic forces. The e-motor designers have to work, of course, on the electromagnetic parts, on the e-transfer parts, but more and more they need to integrate the vibroacoustic part as well. And the thing with vibroacoustics is to really understand the ENVH excitations. They are pretty complex. Their transfer paths are pretty complex as well. The forces can be applied either on the rotor or on the stator. I mean, the noise issue can come from a force on the rotor or on the stator. It can come be due to a radial force or tangential force. The propagation can be airborne or structure-borne. And the noise issue can be due to a resonance or not. It can be due to a specific slotting harmonic or due to a switching harmonic on the machine. And it can impact as well the sound quality, the global sound quality of the product. So that's why it's very key to integrate noise and vibration in the design of electric machine. But the thing is, most of the techniques that are used to reduce the noise on electric machine, they lead to a reduction of the performance of the electric machine. So for instance, if you implement some skew on the machine, it can be better for the acoustic, but you will have an impact on the torque level. So it will always be a matter of trade-off. But to analyze the ENVH, the first thing will be to really understand the generation process of this noise due to magnetic excitation. So the idea is really to start with the current, which is going to create electromagnetic forces on the stator to steep. And those magnetic forces are then going to create the structure to vibrate, which will then create some noise if the noise occurs at a frequency which is audible. So this is showing that to really assess the noise due to electromagnetic excitation, the idea is not to focus on the acoustic, but to integrate the full multi-physics design of electric machine. So for this is important to really understand the source of the noise problem. So usually when talking of magnetic forces, we associate to a given magnetic force an harmonic, a frequency, sorry, so it's associated to a specific harmonic. But we characterize a given magnetic force as well by its wave number. So the wave number corresponds to the spatial distribution of the force along the air gap. So here you have an animation made with Manatee software, where you can see in function of time the distribution of the forces applied on a stator to steep. But actually, these global forces can be decomposed as a superposition of several magnetic forces. Here you have the magnetic forces of wave number R equal to 0. So why it is equal to 0 is because along the air gap, you can see that there is the same amplitude of the force. So here we have an example of pulsating radial forces where the forces are radial, and in the bottom it's a tangential pulsating forces. So it's what corresponds to torque ripple, for instance. And then the combination includes as well some forces of wave number are equal to 1, where you see in function of the circumference, there is one maxima, one minima at a time. That's why it's R equal to 1. And in the radial direction, this corresponds to the unbalanced magnetic pole. And after 1, there is 2. So you can see here an example of a force of wave number plus 2. Where there are two maxima and two minima at a given time. So this is in radial direction again, and you can do it up to a very high wave number. So from there, you see how to characterize a given force. And it's actually very important to identify when dealing with a noise issue. So to have the link between the forces and the noise. So it's what Manatee can help you with. So this software objective is really to improve the NVH performances of electrical systems throughout their development life. So the idea is to make the link between the e-machine geometry and its control parameter to the system level sound power level due to magnetic forces. So Manatee is the only software specialized on the electromagnetic design optimization of electrical systems. It includes, of course, the magnetic vibrations and acoustic noise due to Maxwell forces. So the software provides some predefined simulation workflows, which is very handy to set up quickly a simulation. So some of the workflows are dedicated to early design phase, and other workflows are more detailed. Then it will provide you fast and accurate calculations, and Manatee can be used as well to study the impact of manufacturing tolerance, for instance, and I assess the robustness of an existing design. And it can as well help you to identify the root cause of the noise problem based on automated post-processing you can access at the end of the simulation. And of course, here you can apply specific mitigation techniques such as skewing to reduce the noise of your machine. So this software has been inspired by EOMYS consulting experience, where EOMYS was able to reduce up to 40 dB the noise on a given design. EOMYS has experience on more than 170 industrial cases through a wide range of topologies and through a wide range of applications. So the idea with the software is really to provide an integrated ENVH simulation and analysis environment to electrical engineer, to mechanical engineer, and to acoustic and test engineers. So the current version addresses mainly the electrical and the mechanical engineers. And in the future, we will integrate more features dedicated to acoustic and test engineer. So what Manatee can do as well is able to being interfaced with existing CA tool. So for instance, here it's possible to import some electromagnetic flux calculated with GMAG software. Here from the mechanical side, it's possible to import some modal analysis results calculated with ANSYS, or it can be OptiStruct. And in the future, it will be possible as well to integrate some test data so that a direct comparison between measurement and simulation can be done. And we plan as well to make possible the import of radiation efficiency from Actron software, for instance. So if you have a look at the user interface of the software, just by looking at the icon banner, you get an idea of how to use Manatee. So first, there was a need to set up, to define the machine. And then the idea is to select a predefined workflow to apply or not some tolerances. And then you can save and run the simulation. And from there, you have access to predefined plots. You have an example there, which will allow you to better understand the origin of the noise issue. And once it's done, you can solve the noise problem by integrating specific solutions. So why Manatee is fast and accurate? The first thing to mention compared to general CAE tool is that it's really easy to set up the simulation with Manatee. So even if it's a multi-physics, there are multi-physics model behind, everything is well predefined with Manatee. So there are different workflows. By default, you can select. So some will be more dedicated to early design stage. Others will be more dedicated to more advanced design stage. And you'll see that here you'll get an automatic coupling between the magnetic model and the force model, for instance, between the force and the vibration, and between the vibration to the acoustic. Then, in terms of calculation time, Manatee is very fast. The first reason is from the magnetic model. Usually, the magnetic flux are represented using what we call a magnetic lookup table, which is then allow you to speed up calculation at variable speed. So this is by using flux interpolation or flux extrapolation. Then, from the structural point of view, as it's possible to import model bases from ANSYS or OptiStruct, we've seen that. Actually, the import can be performed offline, so that offline, the software is calculating the response of model shape envelope nodes to some specific load case. So the load case here we're talking about will be the different magnetic forces, for instance, a magnetic force associated to wave number 0 and applied in a radial direction. And then from we'll be using the electromagnetic vibration synthesis here, which is combining on one side the structural behavior, on the other side the magnetic behavior, to calculate airborne and structure-borne noise at variable speeds. So within few seconds, you get access to 100 speed points, even when magnetic FEA and mechanical FEA are used. Then, then another advantage of Manatee is that the post-processing is automatized, and by default you get access to the 4 most relevant visualization. So here, for instance, you see a spectrogram of sound power level in dBA, which is highlighted, together with the order tracking analysis. Then by default here you have access as well to the 2D plot of the forces. We'll come to that a bit in more detail just after. And here is what we call the spatiogram, which is very powerful to understand the root cause of the problem. So you'll get an idea of the load case, which is the cause of a given harmonic, for instance. In top of that, you have as well access to operational deflection shape, as you see here. You'll have access to flux density, to acoustic noise maps, where this time you have you can visualize the sound power level in function of speed, but as well in function of the torque. And then here you can visualize the lump forces applied on the stator teeth. To give a bit more detail, here is the extraction of a 2D FFT of the forces applied on the air gap. So this is in function of the electrical order on the x-axis, which is equal to P times the mechanical order, where P is the number of pole pairs of the machine. So in this case, P is equal to 4. And on the y-axis, it's the wave number, where you see, for instance, that this orange spot corresponds to an excitation occurring at a wave number -8. So you see here on the animation 8 maxima and 8 minima. And you identify as well very easily its frequency. So here 2 times the electrical frequency. Here is another example where this time, as the wave number is 0, you get to see a pulsating force. Then we've talked about the possibility to study some eccentricity defaults. So here on a different machine, you have an example of the order tracking we get without any defaults. And then by applying 20% of static eccentricity, you can see here that there is a new resonance which is occurring. And this new resonance is associated to a wave number 1. And looking at the operational deflection shape at this from this excitation, you see that the peak corresponds to a bending mode. So actually, it's what we would expect. An excitation of wave number 1 being in resonance with a bending mode. Then here is an example of a design optimization. So the rotor can be skewed by different ways. So the skew can be linear, in V-shape, or in zigzag shape, as it's shown. And depending on that, you'll have a different impact on the sound power level. So in this typical example, you see that there is up to 10 dB benefit using the V-shape, but this is very specific to the motor we studied. And you see here as well that whenever the rotor was skewed, there was a negative impact on the torque, of course. So to summarize, Manatee software is a pioneering software specialized in the assessment of magnetic forces, vibration, and acoustic noise. It allows you to troubleshoot and reduce the noise of electric system. And it's made in a way to make the collaboration between electrical, mechanical, and acoustic engineer more easy. And it's developed based on our experience at EOMYS. So this is mainly focusing on simulation, but of course simulation always need to be fitted based on experiments. So I give the ball to Ed.
Thank you for an excellent presentation. Can I just ask you a quick question? Very early on, you mentioned that there were trade-offs whenever you were doing a design and you're picking optimal pull slots and skewing. Those kind of impact efficiency, but is it a large impact on efficiency generally in your design experience?
Yeah, it can have a large impact on efficiency. That's why it's always needed to make some simulation to assess this impact, and as well to to collaborate with electromagnetic engineers to make sure that everything is well controlled.
Okay, thank you very much. Okay, I'm going to, as Corinne did, I'm going to start with an introduction to our company, HBK. HBK is a recent combination of two different companies. First of all, there's Brüel & Kjær. Brüel & Kjær is very famous for microphones and for noise and vibration measurement equipment. It was founded, this slide says about 70 years ago, but it's actually, we're zooming up on close to 80 years of noise and vibration measurement history. B&K has approximately 1,000 employees, and it's located in Denmark, just outside of Copenhagen. The other part of this new company, the H for HBK, is a company called HBM. HBM is equally famous. They have 1,900 employees, and they are involved in electrical measurements, machines that measure voltage and current and efficiency of all different types of electric machines and electric systems. They're also very famous for torque transducers and the measurement of torque, and equally so for the measurement for weighing equipment and strain transducers. So you kind of get an idea of the synergy behind the two big measurement companies being put together to become the new, more powerful HBK. I'm in a group called Engineering Services, and just imagine within B&K 1,000 employees, and they're making microphones and handheld sound meters and all the different types of equipment. But there's also a group of us that provide expanded offering for our customers to provide measurement services, and that's what I do. So there's 16 of us here in Detroit who do measurement services, specializing in noise and vibration. There's 6 people in the UK doing noise and vibration. There's about 40 people I think it's 40 people in Europe doing strain gauging and strain measurements, and then there are also people in a smaller group in Asia that do sound and vibration measurements and do strain gauging. So that's what engineering services. The engineering services part of HBK does, and that's what I'm a part of. I'm lucky enough working in Canton to work in a beautiful lab that we're co-located, and we lease rooms from Material Sciences Corporation. We have a four-wheel drive NVH chassis dyno, a beautiful dyno. We also have 2 hemianechoic chambers that are huge. They're 25 feet by 35 feet by 14-foot roof, so they're big enough to pull a car or a small truck into. But we can also, we do a lot of work with appliances also. We have a fully anechoic chamber, which has the fake floor and the wedges underneath. It's smaller. It's, I think, 14-foot by 14-foot by 10-foot roof, but it's also much quieter than the hemianechoic rooms. And we can, on a typical day, we're 16 or 17 dBA in that room. So it's a very quiet room, and it's great for measuring electrical equipment because it's generally quieter. We also have a sound transmission loss suite, so we have connected reverb and anechoic rooms that we can use to measure sound transmission loss. Okay, why measure to improve noise and vibration? Or you could put this a different way. What role does, if the software can very accurately predict the noise performance of electric machines, then what do measurement people do? What's the role? How do they complement each other? Well, first of all, model validation. Whenever you make any type of model, there are certain assumptions that need to be made and to be validated. Even in mature software, because new designs are constantly coming along, and those new designs challenge the assumptions that need to be made in the model. So we can measure to validate and compare between the real product and the model product. We can do that by comparing natural frequencies, since a big part of predicting the amount of noise and vibration is modal superposition. It's important to get the natural frequencies correct and the mode shapes. So that's one of our roles. Another role is to look at operating deflection shapes, to compare what the model thought the results were going to be and what is actually being obtained. And then also comparing other outputs such as vibration, torque ripple, and sound levels as a function of speed and load. Our BKConnect software has specialized features that allow us to compare the modal results between the CAE model and a real measurement. So you can see my pointer here. If we start out with a fully meshed product, we can parse that down and come down to discrete points, so that when we're making measurements, we are making measurements that correspond to actually numbered nodes on the model. Then we can look at the correlation between the measured results and the predicted results of natural frequencies in a modal correlation table, and also graphically, as shown down here in the bottom right, in order to refine the model to get the best possible correlation between the two. We can make measurements of operating deflection shapes. This is a demonstration that we did on an experimental motor at the Illinois Institute of Technology, where we wanted to see if we could use the HBM Genesis high-speed system to acquire the data and do an operating deflection shape, which we were able to successfully do quite well, where we laid out a grid on the stator and then measured its displacement at a particular frequency. Doing the modal also provides a measurement of damping, which can be very useful. Trying to predict damping and insert it into a FEA model can be very difficult. It's fairly simple to set up an accurate structural model, but if you want to add damping, all of a sudden you need all that detail and all the joints and the connections and in the viscoelastic materials and all of those things. That can tremendously increase the number of degrees of freedom of your model, and maybe to a point where it's not as efficient as it could be. So by measuring the damping, we can take usually those realistic damping values can be inserted into the superposition model and come up with a very efficient structural solution and modal superposition solution for noise and vibration. And the point there being, it's easier to measure the damping than to do all that detailed modeling. Troubleshooting. Sometimes things don't perform as you expect the design to do. This is a result of an 8 kilowatt fan that we measured, where we did a descending speed sweep. So we started out at 100% speed and decreased down to 20% speed. This axis is speed, the vertical axis is speed. The horizontal axis is frequency. And we see here that we have several orders. You know, the diagonal lines are orders. We see this one right here is the fourth order. This one is the fourth order. But our real vibration issue here is this area right here. And we see that basically what we have is the intersection of this first order with this horizontal, with this vertical line, which represents a natural frequency. So we have a 30 hertz natural frequency that's getting excited by first order, which means that we have a combination of a balance issue with a natural frequency that needs to be addressed in order to reduce vibration levels. We can use the acoustic camera to better visualize the noise pattern of electric motor. In this case, we're back to our experimental electric motor at the Illinois Institute of Technology. And this is a visualization of the noise radiation at very high frequencies between 8,700 and 11,000 hertz. We were also able to use this to look and see how much noise was actually being produced by the dyno motor. We can look at the electric machine as a black box and do other things with it too. So in this example, we're looking at the electric powertrain of a car, and we are making measurements on a car that has an induction motor, and playing the what if game and saying, what if we substitute a high efficiency SRM motor, a switch reluctance motor, into that? We know that the switch reluctance motor has much more torque ripple and more vibration in general, but does it produce a drivable car? So we can make a bunch of measurements to characterize the car as a path and to characterize the electric motor as a black box, and then do this virtual substitution in order to see how it's going to be. And then as a final step to determine what type of remediation needs to be done for the switch reluctance motor, and to look at the implications of cost and weight. We have a very powerful tool in the Genesis high-speed system. This is a system normally used to do electrical analysis, and it measures sample rates up to 250 megahertz with 64-bit resolution. It can measure voltages up to 1,000 volts, in other words, from minus 1,000 to 1,000 volts peak. But it also has the ability to take inputs from accelerometers, microphones, and torque meters, and make simultaneous measurements of the real voltage signals, the real current signals being fed to the electric motor, and look at the resulting vibration and noise all in one system, so that we can do traditional NVH analysis such as color maps and ODS, but also simultaneously look at current and voltage. It's very powerful in order to do inverter tuning as a means of improving noise and vibration performance. And finally, systems, you can make 1,000 motors, and some of them are going to be different than others. So our Discom division produces end-of-line systems that can make end-of-line measurements of electric powertrains as they come down the line. 10 years ago, these guys were measuring thousands of transmissions every day. Now half of what they do is electric drives. I think that's, don't quote me on that, but a lot of what they've transitioned over is to looking at electric drives for vehicles and quantifying those in the same way they used to do transmissions. And it also has the power of being able to work with the Genesis high-speed system to look at the electrical parameters associated with the end-of-line performance. So in summary, the role of motor, the role of measurement is we provide model validation, model input in the form of being able to provide the damping to go into the model, troubleshooting, the ability to combine high vibration measurements with electrical measurements, source path contribution to come up with simulations, and end-of-line measurements. Thank you very much. I think while I have the floor, I will also address the EOMYS HBK collaboration. We are two different companies, and we do both have different specialties. So the idea is that EOMYS provides design, they can provide measurements, we can provide measurements. We both have special talents in different equipment depending on the the level of support that's needed. And then the experimental validation was something we'd work together on.
So
you think, Corinne?
Maybe just based on the measurements, the idea would be that we can use EOMYS specialty to analyze the measurements and identify the most probable transfer paths, as you mentioned earlier. And based on that, we could then simulate the design so this time it would be by using Manatee software, simulate the design and validate a potential noise reduction technique that we would pick. And if one of the reduction technique can be implemented, then the idea would then to validate from an experimental point of view the results of the simulation. So this is kind of the whole EOMYS HBK collaboration. Maybe I have one note regarding the end-of-line testing you were mentioning. Applied to electric motor, it's something that is important and that we can use to analyze if there is a default or not on the motor. So for instance, in case of dynamic eccentricity, we would directly see on the measurement spectrogram if there is a problem with that or not. So here is really making the link between simulation and validate and measurements.
Well put. We do have an upcoming event. EOMYS has an upcoming event in January 2022, which you can find a description of at www.eomys-training.com.
Yeah, there are still some places left, so yeah, if you're interested, you can have a look.
Does that have a specific focus?
This is dedicated to noise and vibration due to magnetic source.
And the EOMYS and HBK are also putting together a technical workshop, which would be an in-person event, a seminar, both in Canton, Michigan and San Francisco. We had a firm plan for a date of that, but we had, due to the recent COVID outbreak in the United States, we had to put that on hold. Right now, we're working on dates that are in April. So we'll if you were notified of this webinar, you'll be notified in a similar way for this upcoming seminar.
Awesome. I think we can do a couple questions. Ed, do we have some time for some questions?
Yeah, I think we have about 5 or 10 minutes for questions.
Great. So someone asked, what is the recommended vibration measurement metric for quality control of electric motors? Thinking acceleration versus velocity, RMs across frequency range versus peak at fundamental frequency, etc.
It kind of depends on, I'll kind of take this one on. It kind of depends on the motor, but generally with electric motors, the ones that I've seen, the factories I've been in, there is already some type of electrical measurement to look for to see what the impedance are of the different phases and that type of thing. And then it just becomes an extension of that. I would recommend looking at vibration through a sweep at several different loads in order to characterize it, and also some coast downs. But it really depends on the past history and what type of field history you have and what type of customer experience you know, you really want to tailor those end-of-line tests to very particular issues you've seen in the past and make sure you're addressing those most of all. Sorry, that's kind of a generic answer, but
Awesome. Corinne, did you have anything to add to that? I have
yeah, maybe just the fact that here we regarding vibration measurement, we analyze them mostly in velocity, so in meter per second, to get because this is more how do you say? It will be closer to it will give you an idea of the acoustic, because you know that the acoustic power is proportional to the velocity squared. So we prefer to visualize vibration measurement in velocity.
Yes,
awesome.
and that's generally how the discom systems work too. They measure vibration. It's just so much more reliable and produces so much better signal to noise than trying to make acoustic measurement in a factory environment.
Now I have a question here. What is the relative importance of airborne noise and structure-borne for a motor?
Yeah, from our experience, I would say it's really dependent of the application. It can be different from a motor to another one. But what we can say is that, you know, the pulsating forces, when they are tangential, they are likely to have an impact on the structure-borne transfer paths. And it would be the same for wave number equal to 1 or -1. So it's what we call the average forces. Those are likely to have impact on a structure-borne path.
Yeah, you're talking about, we could call those torque ripple.
Yeah.
Yeah, it kind of depends on the vehicle, but it's becoming obvious that it's depending on the motor type, as the motors go to higher performance and more efficiency, the torque ripple generally becomes more of an issue, and torque ripple is structurally carried, right? It comes through the engine mounts, but it also comes through the suspension, because for the motion of the engine mounts, there's an equal and opposite reaction on the suspension. So that's it. And also, you know, it's a constantly evolving situation too. You know, direct noise radiation from an electric motor can be important, but it depends on whether it's been treated or not. I've seen a lot of electric motors lately with acoustic treatments on them. So if the motor is already acoustically treated, then certainly that increases the role of structural borne vibration.
Awesome. I think we have time for one more question. Ed, what would you say?
Yeah.
Okay. If the acoustic camera shows a radiated noise hotspot, what can be done about it?
Oh, that's an easy one. Thanks for giving me an easy one to wrap up here. Like I just mentioned, you can actually put an acoustic treatment on a motor. A few years ago, I thought that electric motor manufacturers would be very resistant to putting any type of, you know, acoustic treatment on them, but it appears that's not the case. That as long as it's properly designed, that they are willing to do that. They are willing to put these fairly thermal insulating systems around to block the noise that comes off of the electric motor. So that's actually becoming pretty common.
Great. Here's another one. How good are prediction methods for both performance and noise?
That's all you, Corinne.
Yeah, thanks. So yeah, prediction methods, it depends how the model was set up, but usually there is always a need to fit some specific parameters in the model, and so the results will depend on that. So what we've seen with HEAD today was the importance of measuring the damping, for instance, to then be able to fit it in a simulation, or to measure some structural modes via an experimental modal analysis, to then again fit the structural model. And from the magnetic side, there is the BH curve, which is very important. So yeah, you know, a simulation can give you many results. It really depends on how you specify the parameter, and usually some measurements are needed to make it better.
I think it's worth mentioning that motor design is evolving very quickly. That while maybe 10 years ago we saw things that were pretty much induction motors and things that were pretty much permanent magnet motors, now we're seeing all types of variants and hybrids on that. And you know, certainly with the tremendous influx of new designs, that adds to the challenge of properly modeling and being able to and the predicted fidelity of the models.
I think this one, Corinne, is directed to you. Is it possible to simulate the effect of other mechanical faults in electric machines on the NVH?
So the other mechanical faults, is that right?
Is it possible to simulate the effect of other mechanical faults in electric machines on the NVH?
So yeah, it depends what is meant by mechanical faults. So at the moment, with Manatee, we can handle eccentricity problem, uneven air gap problem, and in the future, uneven magnetization or pole misplacement. Maybe pole misplacement can be a mechanical problem, so it's again dealing with tolerances. Yeah, but of course, you know, if it's questioning, for instance, the noise coming from a gear system next to the electrical motor, then a separate software will be needed.
We could keep going with this, but I have to jump off right now. Thank you, everyone.
Sure. Yes. I think that wraps up the questions anyways. Now, I know Ed just had their contact information up if you wanted to reach out to them directly with any other questions. We want to thank you again for joining us. There is a post-event survey if you wanted to request any more information from your presenters. So thank you so much. Thank you again, and we look forward to seeing you at the next webinar. Bye, everyone.